Well, as we explained before, the inertia constant is a very important parameter inside the power system because it has a very profound or very deep effect on the power system dynamic. Okay, especially today with the with in modern power system, one of the problem has been the sudden reduction of the inertia. Okay, and one of the things that we identify is that the inertia is affecting almost every single variable inside the power system. However, today we are working only with classical power systems, and today I am just concerned about power angle. And for sure, 100% sure, inertia constant have a very important effect on the electromechanical oscillations of the synchronous machine. Well, it's clear. It's because it's clear that it's amplifying or reducing the acceleration of the synchronous machine. Okay, but the first thing that you need to understand is that in electrical power systems, we don't have a single electrical machine. We have many electrical machines. And as consequence, we need to use multiple swing equations, and every single generator have inertia, and synchronous generator, they have inertia, and this inertia is basically defined on the nameplate characteristic. And when we are working in electrical power system, we need to refer all the quantities to per unit system on the same basis. And that is one of the interesting things new for you. Okay, you have been working, my student has been working with per unit system for many years, but the calculations that you have done are basically electrical quantities. Now, inertia constant is mechanical, electromechanical constant, and also must be referred to the same base. Okay. Here and at the left side of the screen, you will see that there is an equation, and that is the equation that we use to change base for the mechanical inertia that you have. Over here, what I am saying is that the new per unit system, it will be the all multiplied um, by the by the nominal power coming from the generator and divide by the base. Okay, what I'm trying to say is that it's typical that we refer all the inertias to the same basis. Okay, and to do so, we need to have inertia, sorry, a power base for the whole system. Okay, some people say and some books say that the whole base of the system is basically the 100 MBA. But however, that is not a rule. Okay, what I want to say is that using a base for the whole system is what we do, and that is what you need to understand, that every single inertia constant inside the power system must be referred to the same basis, and over there you can find the equation. Okay, why we prefer use inertia constant h instead of m or j or I? Well, there are many reasons, but one of the things that you must understand is that the inertia constant is a more electrical or more power system parameter. Okay, because it's relating the kinetic energy that you store in your rotors at synchronous speed with the rate power of your generation unit. From the power system point of view, that makes sense. That is more uh, it's realistic in terms of the understanding from the power system point of view. But another interesting property of the inertia constant H is that first, the range of variation for the inertia constant is relatively small. I mean, if you are working in a power system and is using real units, you will realize that the inertia constant is inside a very narrow range of value. Here at the screen, you can see there is a table that depending of the type of machine, you will have different inertia constant. But without so much explanation, what you can see is that the minimum inertia here is around 1 and the maximum is probably 10. What I'm trying to say is it's very, very simple to detect mistakes because the inertia constant is inside a very narrow range of value. The other thing that you must understand is that the inertia constant depends of the type of synchronous machine. Why? Because depending of the type and depending of the size I means the MVA, the rate power, depending of the size and depending of the type of machine, rotor or salient pole rotors, you will have different inertia constants. And the reason is because the weight of the rotor, the shape of the rotor, they define the inertia constant. Okay. Over there, you can see that for very small synchronous condensers, you can see that the inertia is between 1 and 1.5. However, if we are working with a slow rotational speed, turbine generators, while the inertia constant could be a bit bigger, between 9 to 6. Okay. Again, and this table is just for illustrative purposes. However, uh, uh, for any synchronous machine that you are using for studies, please refer to the manufacturer and get the proper information and get the proper details about the inertia constant. The inertia constant is extremely important because it's defining many of the characteristic of the oscillations in the dynamic process inside the power system. For that reason, be careful when you are including the inertia constant in your future stability studies, okay? What I will do now is I will go through some specific applications and specific cases of the use of the string equation. Okay. Um, Later I will tell you more about the reason, but when you have many generation units working together, each generation unit have a swing equation. Okay. Uh, what I'm trying to say is a multi-machine system, when there are many synchronous generators, you will have as many swing equations as many generators you have in your power system. For instance, over here, you can see on the right-hand side that I am presenting two generation units connected to a bus bar, and each generation unit, it will be represented the electromechanical behavior of each generation unit. It will be represented by a swing equation. Okay. And what I want to do today in this very specific moment is, okay, what's happened if we have two synchronous generators inside the same power plant? Can we obtain an equivalent machine? And the answer is, well, depend. Okay, depend. But let me start with the case that I say fully yes. Well, yes, if we have two synchronous machines connected in that way, we have two swing equations. I believe you can see that we can add this equation with the other equation. It's very simple, and we can obtain a single equivalent machine, okay? What will be the solution? Well, the solution is, as you can see, the inertia constant must be modified to represent the two machines. The mechanical power and the electrical power also, they must be modified in order to represent the new equivalent machine. But more important is that when we have two machines, each machine have a power angle. And you must remember that this power angle is referred to the synchronous reference, okay? What I'm trying to say is those angles, they are measured against a reference, and that is the synchronous reference, okay? A vector that is rotated at synchronous speed, and all the angles are referred to that angle. However, when I am calculating this equivalent machine, as you can see over here, because I am adding those equations, I must say, okay, the angle 1 and the angle 2, they are the same angle. What I'm saying is that the machine swings together, and if the machine swings together, I can get this equivalent angle over there, okay? What I'm trying to say is if we have machines and they have similar characteristic or identical characteristics, and they are connected to the same bus bar because they belong to the same power plant, I can get an equivalent. But in this case, I am assuming that those machines are similar and they swing together. When I say they swing together, what I am telling you is that the power angle of those machines are the same. And we call that kind of machines coherent machine. Coherency is a property of the dynamic, coming from the angles and rotational speed. When machines they follow each other in terms of angles, we say that they are coherent or they swing together. Okay, but there is a case. What's happened? What is the case if we have machines that they are so different? For instance, one of them is huge and the other one is very small. What's happening in that case? Well, in that case, if those machines are not swinging together, if they are not oscillating together, that is the case that we call that non-coherent machines. And non-coherent machines means that those machines, each one of them have a angle delta 1 and delta 2, and we cannot say that those angles are similar. In reality, those angles are very different because they are not coherent. What is the only way that we can solve this problem? Well, we can try to find an equivalent machine. And what we need to do, for instance, is dividing each equation and using some coefficients, and then multiplying by this relationship about the inertia. And then we will got this big equation over here. Okay, what is this big equation over here? This big equation over here is defining how the difference between the two angles is changing when we have some electrical and mechanical power in each generator. I believe you can see by simple examination here that we can convert this into the equivalent inertia. This term here is only including mechanical power, and we can convert that into an equivalent mechanical power. And this term here, the negative term here on the right hand side, represent electrical power, electrical power, and we can say that is an equivalent electrical power. What I'm trying to say right now is that we have here two non-coherent machines, and we are obtaining an equivalent machine. Again, we can use the swing equation, but right now we will use the swing equation. We will use the swing equation at the equivalent machine. And what we need to be very careful is with the definition of the equivalent inertia constant, equivalent mechanical power, and equivalent electrical power. Okay? Okay. Now we can obtain this equivalent generator of non-coherent machines. But the important part here is that you look here. The angle that we are obtaining is the difference between delta 1 and delta 2. What I'm trying to say is when we are using this approximation, now the angle that we are obtaining is not an angle referred to the synchronous reference. The angle that we obtain here is the difference between the two angles. However, the good news is in this case we can use this difference between angles in order to analyze the stability. Because if there is a problem of stability, the difference between those angles will increase or will oscillate as we described before as instability. Okay? Okay, something that is very interesting is that sometimes we used to define one of those angles as reference machine. As I said before, those machines are very different. But what's happened if one of them is extremely different and we call that machine infinity boss? Well, to be honest, in this class, we will use the concept of infinity boss a lot because it's one way that we can compare the behavior between a big generation unit with a normal size unit. But the concept of infinity boss is mainly related with first is a generator that have so big inertia. To be honest, is infinitive inertia that the frequency is constant. The angle position is constant. And as a consequence, voltage magnitude is constant, and at the same time, the angle is constant. What you need to understand is that the infinitive boss is a very useful concept that we will be using in right now here. But this concept is coming from the fact that this machine have so big inertia that we can consider there are no changes on angle, there are no changes on rotational speed. Okay. Okay. Now I need to keep moving. Now I need to keep moving to explanations related with equations that we will use for uh, uh, calculations of on power system stability. Okay, power angle stability. One important concept, I think all of you must recognize there is a very famous equation that received the name power angle equation. Okay, my student must recognize this equation has been used in the past. All of you have used this equation probably in the course of transmission systems. There is a strong relationship between active power and angle. Okay. What I will do now is I will go through the swing equation and I will try, well, I will not try, I will do a full explanation how to include this term over here in the swing equation, the electrical power in the swing equation, okay? The first thing that you must understand is that here in this class, we are dealing specifically with transient angle stability. And transient stability means a time frame that is very short. And we can say that in that time frame, we can assume that the generators are so slow that they are not affecting, they are not working inside the time frame. What I'm trying to say is the governor is the controller that is acting on the mechanical power of your synchronous generator. The governor has many time constants inside, and what I am saying at the moment is when there is a short circuit, for instance, this machine, the phenomenon is so fast that those times constant of the generators, they don't allow the generator to respond inside the time frame that we are interested. For that reason, if the governors are not acting inside this time frame, we can say that the mechanical power is constant. What I'm trying to say is this is a very conservative assumption in this case for assuming that the governor is not working, okay? Mm, in real life, the governor is acting, however, is probably neglectable the action, especially if we are working with very big generation unit with a lot of inertia. But if we were working with very small system, isolated systems with very small inertia, please don't take for granted that the governors are not acting, okay? If you are working in a very small village and there is a diesel generator, two or three diesel generators working together, please be careful, okay? However, here, if we are in classes, we will assume that the mechanical power is maintained constant, okay? What I trying to say is that this number over here is constant because the governor is not acting. That means that the acceleration power is mainly coming from the electrical power. The electrical power is what defines the acceleration of the synchronous machine. And that is the reason that I need to define a proper equation to identify the electrical power changes when the machine is oscillating, and that equation must come here inside the swing equation, okay? What you need to understand if we are in a steady state, the electrical and mechanical powers are equal and the machine is not accelerating. All of you must remember if we are interested on transient stability, well, right now we need to use the transient model for the synchronous machine. During my classes of short circuit analysis, I introduced three different simplified models for the synchronous machine: round rotor, unsaturated, blah, 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 blah. What I'm trying to say is there are at least three models: subtransient, transient, and steady state. In this case, I am presenting over here the steady state model, but representing the subtransient behavior, okay? You can see over here that the reactance that we are using is the the transient reactance, and here the internal voltage of the machine is the transient voltage, okay? Later we will say that we assume that also the AVR is not acting and this voltage will be equal, numerically equal to the uh, numerical equal to the steady state voltage, okay? And on the right hand side over there, what you can see is the very beautiful phasor diagram. You can see here the very beautiful phasor diagram of the machine, okay? In this case, you can see the reference. This is the rotating reference as synchronous speed, and delta is the angle that is defining the position of the internal voltage of the synchronous machine measured from the reference rotating at synchronous speed, okay? Okay, by I still in the challenge of defining an electrical power here to be included inside the swing equation. And what is the best way to do it? Okay, let's imagine that we have the synchronous machine delivering power to a big power system. Okay, if we have a big power system, that big power system is receiving the power through this transmission system. And this transmission system, the good news is a very simple system. Probably the topology not so much. My students, they are quite good. They are excellent on matrix analysis applied to power systems. And they recognize that the transmission system is very simple because it's linear, it's passive, and you can use over there the famous admittance matrix to represent the system. Okay? What I'm trying to say is that we can have a very complicated transmission system, but at the end, if we assume that there is linear passive components over there, we can create a model to represent the network as a multi-port network, okay? And that is what we do when we use the model of admittance matrix, okay? The admittance matrix is basically a matrix that is representing the interactions, electrical interaction between voltage and currents at all the terminals of this multi-port network, okay? In this case, we are assuming, let's assume the following. Let's assume that the terminals conditions, they are the internal voltage of the generators, okay? For simplicity, I am presenting the case that we are assuming this one is a generator and this one can be a motor, okay? And what I want that you understand is that if we are working with only two generators, well, the admittance matrix must be a 2 by 2, okay? The 2 by 2 matrix can be used to define one beautiful equation that you must know from power system analysis, that the voltage of any bus bar can be defined, the voltage at any bus bar can be defined by this equation that receives the name power balance equation. The power balance equation is basically saying that the power that is injected by the generator is equal to the power going through the transmission lines, and the power that is going through the transmission line is described in terms of the admittance matrix elements and the terminal voltages. That is what this equation over here says. If we use polar representation, you can see here the polar representation. This is a very compact way to see the power balance equation, okay? In this case, I separate the power balance equation in two components, one representing the active power component P, and the other one representing the reactive power Q. Uh, One simplification that we can do over here is saying that the angle between the bus bar 1 and 2, they can be defined like we can create a new angle delta that is defined like the difference between the angle 1 and 2. We did something similar a few slides ago. What I'm trying to say is we are considering a angle that is a relative angle between the two machines, okay? And then using this gamma as a property here, we can obtain, again, a more compact way to represent the power balance equation, okay? In this system, I am interested on the power angle relationship. But in this case, I am really interested on the active power. What is the reason that I am interested on the active power? Well, basically because the swing equation depends on the active power, and for that reason, I will not take in account from now on the reactive power. Okay, I will focus only on the active power. The thing is, if I focus on the active power, you must realize that the equation that is here from the power balance, they can be rewritten in the following way. We can say that the electrical power, has two components. One component that is constant and is coming from the losses related to G, and the other one is Pmat that is coming from this product between voltages and the admittance. Okay. What I need that you understand is at the end, the power balance equation is telling me that the electrical power that the generator supply has mainly two components. One related with some losses that later we will say the system is lossless and that component will disappear. And the second component, as you can see over there, we can say that the coefficient is constant if the voltages are constant, of course. The coefficient P max 1 is constant if the voltage B1 and B2 are constant, of course. But what is important to see is the second term of here is a sign that depend of the power angle. What I'm trying to say is that beautiful equation on the top over there is